along with Dr. Gamble's talk? Yeah, all right. All right, some hype for our next speaker. All right, so our next speaker is Dr. Ron Gamble. He is an Afro-Latino astrophysicist, science communicator, and artist. He sits at the intersection of theoretical studies of relativistic jet emissions under the lens of general relativity and creating programmatic advancements that tackle inequities for minorities in physics and astronomy. That was a lot of big words, so please give it up for Dr. Ron Gamble.
All right, how's everybody feeling? You feeling good? Did you drink enough? Come, get another one. All right. So, did everybody hear me in the back? Yeah, on time. Nice. All right. So, this is not going to be your traditional slides. I turned this slide deck. We're going to learn about black holes, we're going to learn about jets, a little bit about spacetime, a little GR, not too much. There's some equations. Sorry, I'm a theorist. But essentially, why do black holes die, right? So I'm Dr. Ron Gamble. I am an NASA theoretical astrophysicist. I wear a whole bunch of other hats that we can talk later about. But we're going to go through a little bit of these slides that I put together. It looks like a favorite comic book. So, let's go. So, take a fast forward. I'm at NASA. I'm also research faculty at UMD College Park. Anyone from UMD here? DC area? Let's go. All right. So what do I actually do? Well, I theoretically, right? So I theorize scientifically possible predictions of new physics as far as black holes, quasars, relativistic jets, AGN, and its autoplay. Okay, and naturally occurring phenomena. So what do we do as theorists? We take what you observationalists, other STEM majors, chemists, mathematicians, engineers, everybody else, we take those things, we put it together naturally, we put it in like a theory blender, we come up with new theories, right? So I use a combination of a lot of other mathematics. Anybody else? Does everybody know about GR, general relativity? Everybody use a supercomputer before? Anybody in Fortran? I'm gonna lose! You get no drinks for less than now. No food. Alright. Do we all drink coffee? Awesome. So very quickly, who has seen these equations before? Nice. Alright, so without any further introduction, we know the Einstein field equations are what governs GR. We know we gotta go for some funky integral that looks like this. So this equation will actually describe the geometric variation in space-time. Right? So what do we mean by that? We mean that the gravitational motion of test lines with dust, galaxies, planets, exoplanets, stars, AGN, dark matter, dark energy, my mom, whatever, they all have to succumb to space-time and how it behaves, how it curves, how it bends, right? How it ripples. Anybody else study gravitational waves? All right, they do that in grad school. Now, what we actually mean by a black hole? Well, we're talking about this. So if you're looking at, anybody ever study or observe M87? Okay, couple. So this model you see right here is actually true scale, the toy model of M87. This was done in Mathematica, and there's about 10 million data points right here. So you look at that data, not just a picture. So this is what we do kind of as theorists. But more importantly, putting together the geometry, the math, the physics, and the observational data to tell us story to give more information about what the black hole is doing. No, I don't know what's inside of the black hole. Or my coffee bud in my office right now. Okay. So, now, very importantly, we're all talking about curvature, right? Whether it's curvature around a spherical object, a plane, a disc, whatever it may be, we're talking about the curvature of space-time. These are not the equations you were looking for. But very quickly, those are the components of what we call the curved space-time. Anybody else study rotating black holes? You are my favorite people. So, of course, we have three other types of black holes. Short, shallow, non-spinning, curved, that's spinning, that's uncharged. Curved Newman, we got Newman black holes, and those are charged. We're not going to touch on those. We're not touching on normal. Sorry, guys. I know, next talk. But we are talking about black holes and their relationship to the jets that we get up here, the system that we get. So now, how do we actually extract information or energy from a black hole? What we have to use is called either the Penrose-Williams mechanism or the Blanford's-Diet mechanism, right? So these things are talking about the rotational influence of a black hole and things that are circling around going in. So if you think of just like a blender, if you put something in that blender, it ain't coming out, right? Now, but you get a nice flavored, maybe banana strawberry smoothie on it. Maybe put some rum in it if you're at Astronomy on tap. Right? And then you get something that comes off of the black hole. It's not coming from inside, of course. Optic censorship is a rule. But it is coming near the horizon. And near the horizon is very important when we're talking about relativistic jets and AGN and black holes and that dynamic. Alright, so now let's keep continuing the story. This is actually a pretty accurate visualization of what a black hole would look like if it was ripping through space-time. So, to tell a little story here, I have a little story about the Sherman department chair and another grad student trying to harness the energy from a black hole. What do we mean by harnessing the energy? Whenever we observe a black hole or an AGN or a disk or a jet, we're actually taking information from it. So all the photons, all the electrons, everything, all the information that we have from our observations is actually information that that system is sending back to us. So if you use Fermi, HP, Prism, James Webb, Hubble, Chandra, Swift, all of those, we are collecting information from the black hole that tells us the story, right? So now, let's initiate the model for the black hole. Why did he write this in Fortune? I have no idea. Alright, so now, we're looking at the piece of the one block of code that actually works right now. Now, what do we actually get? Well, we get something that looks like this, right? So we get particles that are circling around the black hole. And this is solved in 4D, right? So this is solved in 4D. Of course, I have to give you a 3D projection. So it can't be in 4 dimensions in space-time right now. But if we're looking at the black hole, this is what the particle motion in 4D is looking like. So you're looking like a 3D model, a 3D solution of what particle pairs around the black hole do. This is for electrons and positrons, right? So electron-positron pairs. So we're talking about high-energy emission, gamma rays, X-rays, and possibly some photron radiation and radio waves, right? Everybody study X-rays, gamma rays, radio waves, infrared, UV, cosmic rays. To show you how complex the relationship is when we're writing these down on paper, right? So sometimes we take for granted when we're taking observations of these systems how actually complex the physics is. We're solving these things behind the scenes. We're telling our computers how to solve them, but to solve them by is actually a different story. It gives you a different story. It gives you a more intimate relationship for what the physics is telling you. Now, one day, we'll learn the power of filtering. Okay, so now, can we actually get to a black hole? Yes or no? No. But what we can do is observe the black hole and again receive information that from what the system is telling us. Play, yes. What comes off of a black hole? Well, that is what we are deeming as a relativistic jet. So it is a jet of high energy particles that's coming off the black hole. And that is what we are considering how the black hole shines. Right? So when we say, does a black hole shine? Well, yes, it does. It's giving us information. It's spewing out all these high energy particles at near the speed of light, if not 99.99999%. And all the decimal places matter. Has anybody ever calculated a Lorentz factor before? Has anybody broken their computer calculating a Lorentz factor before? More than the math. Okay, so now, who has studied the blazar TSX 0506? Just one. Me? Cool. That's none. That blazar is known to be highly variable. What do you mean by highly variable? Well, just like you saw the jet that's coming off continuously, sometimes the black hole in the jet bursts. It's spewing out, sometimes it'll burn extra particles out, or it'll give us extra photons or extra energy. That is what we're talking about flares. This particular blazar is flaring on the minute to hours time scale. So we're seeing these very high energy jets burn on an hour time scale. So this is happening very fast, very high energy, and we're capturing it in real time. Sometimes we can capture them using movies or time domain observations. Now, if we were to really describe what the particles look like around the black hole and they're shining, they're kind of looking like this. So you're kind of looking at kind of a smearing of what the magnetic field lines, what the current lines from these particles are doing. So all of these blue and red lines are looking at all the many different paths the particles might take. So orange 3D model that you saw is very similar to what you're seeing here. So imagine all these particles flipping around the black hole, and then eventually they spew all the way out. Now we're talking about these jets are on the orders of millions of parsecs long. They are wicked long. Now, if you've not realized before, the chairman is a department chair, and the grad student number 4 is, as we know, we've been grad student number 4 before. Now, can we actually harvest the energy from the black hole? No. We would explode. We would explode. You can't do it. Yes, and I'm still finding the minus sign in my book. Alright. Now, can we actually see what a blazar looks like? Yes. This is TSX 0506, the current blazar that I'm studying. Currently looking at the spectra, the observational data, and particle motion around that jet that's pointing right at us. Are we in danger? No. It's just the jet is pointing at us. It's too far away to actually impact life on Earth. You can breathe now. That's it. Now, yeah, looks like they screwed up. I'm out. So, what's the... networking, we're going to do hackathons, technical skills, SciComm, university chapters, just like SPS. Now NASA has them, and a whole bunch of other things. So sign up, reach out to me if you want to. Awesome. I have too many hats to do many things. I have to plug another project that I'm a part of from the Scientific. I'm doing it together with my very beautiful girlfriend, Dr. Raven Baxter. You might know her as Dr. Raven, the Science Maven. She is amazing. Go follow her. She's been everywhere. But we are trying to build, again, the dream of having a career in astronomy, getting students and families interested in STEM, and removing the barriers to do so. If you want to support what we're doing in our nonprofit, you can scan that QR code for more information. You can reach out to me. You can reach out to Dr. Baxter. We're going to be here. And we're trying to get telescopes to families. That's the goal. All right. Now, last but not least, I got to give a shout out to my mother. She's awesome. Thank you, Mom. She kept telling me, this is one quote that I always put up in some of my talks, that, my mother always told me that you can become absolutely anything you put your mind to, whether you're an artist, scientist, educator, but don't forget who you are. Now, as you can see, I made the majority of the artwork in this presentation. So I told my mom, well, I'm just going to be all three. Alright, so thank you for your time. You can follow me on Twitter, Instagram, email, my website, and we are open for questions. Thank you.
All right. Okay, so that was a phenomenal talk. Those are the most unique slides I've ever seen in my life. They're absolutely phenomenal. I'm going to use that word a lot. But let's give it up. Let's get another round of applause for Dr. Ron Gamble. And once again, let's give it up for our maestro of questions, Eric, who will lead our question and answer. Remember, if you want to submit questions, use that QR code. If you want to shout out, let us know. And yes, make sure you send those questions on the QR. Give it up, Eric.
Real quick, we're going to take a selfie. Okay. Does anybody have any questions?
I've got something here on the Google Doc. Excellent talk. Thank you very much. So the first question, and one that I want to echo, is from Emily. Emily, raise your hand. All right. They and I want to know, how long did it take you to make those names on the slides?
Oh my gosh. I would say probably a lap time. It took a few days. It took a few days. Creating the artwork for it only took like a day. Yeah, but I've been painting for 18 years. So I'm an oil painter by training. I was a double major in fine arts and physics in undergrad. I'm a minor in fine arts. I'm doing graphic design. So all of that, yes, I can do that in a day. Maybe some of you can do it too. But I also encourage you to put some of your other talents into your presentations. This field is very multi-talented and multifaceted. The STEAM aspect is very important.
Awesome, thanks. So Isaac wants to know what kind of high-energy photons, like gamma or X-rays, are emitted from the supermassive black holes in the center of spiral galaxies.
Wow, so it's all types. So these AGMs are emitting in every single spectra in the electromagnetic spectrum, from radio all the way up to cosmic rays to ultra-high energy cosmic rays. So with all of them. My particular work is focusing on the non-thermal spectrum. So we're talking about radio, which is synchrotron radiation, right? We're talking about X-rays, gamma rays, and possibly some gravitational waves. Oh yeah.
Very wide. All right. Isaac, raise your hand. We'll get you a little token of appreciation. Second floor. Thank you. simulation to account for the magnetic field.
Yes. Yeah. So actually, so what you saw, some of these equations that you saw are solving Maxwell's equations in curved spacetime. That's where I'm starting. So and then we're going forward. Yeah. So that's where I'm starting from. The goal is to be able to incorporate observational data for polarimetry, X-ray polarimetry. That's the goal. So I'm watching XP, I'm watching Prism that's going up, all these extra X-ray missions. I'm a part of the Christian Explorer missions, a new X-ray mission concept that's going to be on maybe 2040. But that's the goal, to incorporate the magnetic information for polarimetry.
All right, we've got one anonymous question.
Okay.
You can still raise your hand if Scout's honored that it's your question. We want to know what's your favorite thing about gravitational waves.
Okay. So I studied gravitational waves in grad school. I did not need your wave theory. Came up with like 3 different modes of gravity. Go read my dissertation if you want 9 minutes. But my favorite aspect of gravitational waves is the fact that they can permeate anything. So you are literally having a gravitational wave go through you right now. That's just me.